Question. A sphere of mass m radius r is released from rest at a point A on a track in a vertical plane. The track is rough enough to support rolling between A and B. From B onwards it is smooth. The maximum height attained by the sphere from the ground on its journey from B onwards is. From B onwards to what height it will rise. So when it is coming from A to B, the total potential energy due to gravity, whatever it has, that will convert into kinetic energy of translation and kinetic energy of rotation. So by the time it comes to this point, it will acquire an angular velocity as well linear velocity. Now from here on, that angular velocity cannot change because the surface is smooth. So the total potential energy will be the potential energy at the highest point plus the kinetic energy of the rotation what it has. So for getting the kinetic energy of rotation, first step what we should do is to calculate angular velocity at point B. At point B, let us consider. So this height is given as h. So m into g into capital H should be equal to half of m into the velocity of the center of mass at point B whole square plus half of moment of inertia ICM plus into omega square. Omega is the angular velocity of the disk. So this will be half of m into v square. So it can be written as omega square r square plus half of moment of inertia of the sphere 2 by 5 m into r square into omega square. So we can write this one as 7 by 10 m r square omega square is mgh. So simply we can get the value of omega square as 10gh divided by 7r square. Right? We got the angular velocity omega at this point, at the lowest point, point B, as under root of 10gh by 7r square. We can also calculate linear velocity by substituting omega value here. Vcm is equal to V is equal to R omega. We can get the linear velocity at this point. But as it has the potential energy here, suppose it goes to another height. Let me consider this height as small h. So potential energy here will convert into potential energy at this point plus since there is a slipping here, so only angular velocity we have, so kinetic energy of rotation. So let us say it rises to a height of small h. So potential energy at this point mgh, potential energy at this point mg small h plus moment of inertia about the center of mass into omega square, half of I omega square as the kinetic energy. So at highest point mg capital H is equal to mg into small h plus half of moment of inertia of center of mass into omega square. So this will be written as mg capital H is equal to mg small h plus half of 2 by 5 m into r square into omega square. What is omega? We got it 10gh divided by 7r square. Omega square value is this much. So small h can be written as capital H into 1 minus 2 by 7. That will be 5h by 7. Small h is 5h by 7. So at a height of 5h by 7, it will be still rotating with an angular velocity, but it rises to a height of h. So correct option will be h is the wrong option. 5h by 7 is the correct option. 2 by 5h is wrong option. 2 by 7h is wrong option. So correct option will be 5 by 7h. This is the option what we have to consider. So what we have done is clear. We have calculated angular velocity at the lowest point. Okay, when it is rolling down from here, the height h, angular velocity will be omega, linear velocity will be, from here it rises to a certain height. We have taken that value and substituted it in this case, 5h by 7.